There's not that many left. So we talked about inherent error. We'll talk about operational error also in a second. But this slide actually goes to some other slides we discussed previously about the accuracy on a map versus the scale that it was digitized at. And so here are some national map accuracy standards. Proper digitizing procedures were followed. So in general, if a map was digitized at the scale 1 to 1200, you can expect an accuracy of features within 3 feet. Think of that map of Sapporo, Japan, with the 4 different scale maps and how different of a level of accuracy you could expect depending on whether, so you trace the road off the 1 to 3 to million map versus you trace the road on the city map. If you trace a feature at 1 to 100,000 feet, because of the dimensions of the map, you can only expect accuracy of 160 feet or so on. Because, I mean, just the width of your pen, if you're tracing, represents more real-world space. What I won't do is ask for exactly, what's 27.78 feet, but I might ask for the relationship between accuracy and scale, which is this inverse relationship. So as map scale decreases, inaccuracy increases. So it says you go to a decreased map scale, in other words, a map scale with a higher number, the inaccuracy decreases. A large-scale map will, assuming the same protocols are followed as far as digitizing, we'll talk about that. As you go to a larger scale map, the accuracy increases. The margin of error decreases. Hopefully that should be self-explanatory. So a good question is, what is the relationship between map scale and accuracy? So that was, we've talked about inherent error before the break. Now we have operational error. These are actually errors that were introduced during the process of creating the map. So this isn't map projection or using data that's too old or not complete. These are actual errors in the creation of data. And we'll talk about data manipulation causing this error, storage of data, and data entry. So operational errors are quite different. Data entry, here's my GEO. That might be, I even thought of a good bonus question. It might be, no, that's actually a legit question usually on the second test. What does GEO stand for? I have to think of a good bonus like the 100th meridian on the first one. Data entry, typos, simple things like that. I meant to type, what's the population of Lockport? I meant to type 90,000, I typed 900,000. Data entry can introduce all sorts of errors. Data storage, numeric precision. I want to store, you might have done this even in Microsoft Excel. I measure the concentration of PCB to the 100th decimal place, but I try to enter it into a column that only is an integer, a whole number. So I lose accuracy by trying to enter data that's more accurate than this database that's containing it. That makes sense? So instead of 4.783, if the data precision, numeric precision is not that accurate, I might just end up with 5. And so that's an operational error. So when you first set up your database, make sure that it has enough precision to store the data that you want to store. You could actually tie that, and locational precision is kind of the same thing. You could tie that back to that very first slide where we had the map of the world with Chicago located on it. Sampling interpolation, we'll talk about that, can cause data errors as far as conversion or overlay. And output accuracy can only be as accurate as the least individual layer, or the weakest link. So if you're doing an intersect, which I haven't talked about yet. If you're intersecting 3 layers, this is my ideal soil. You want to build a building. This is the ideal zoning, industrial. And you want to build it near the road. We'll talk more about intersect, but basically an intersect would be look at these 3 parameters and where are they all in common? There. that area is by the road that we want, it's in the right zoning, and it's in the right soil. It's not in a marsh. That's great, but if one of those layers is wrong, it throws off the whole analysis, even if the other two are good. That makes sense? So if this road isn't really there but is up here, it doesn't matter anymore that the other layers are very accurate. The weakest link throws off the entire analysis. The output's only as accurate as the least accurate layer. Sometimes error might be introduced purposefully. And if you're not aware of that, you may misinterpret something that was purposely done. Homeland Security, up until a few years ago, many of the GPS services that we all use that were first started by the U.S. military, and they would actually purposely distort the data because they didn't want people to use very accurate readings. It was President Clinton in 1999 or 2000 that just before he left office, did away with that policy, and that caused the explosion in consumer-grade GPS products because now they could be more accurate. I can't show you this, they don't do this anymore, but especially right after September 11th, the Google imagery, they used to make Google do this, they would distort images, and it was kind of a failure. We don't see that anymore. Because they were afraid that terrorists or people with bad intentions would use online imagery for doing bad things, they would actually, it's not like that anymore, they would blur out areas of the map where there was something sensitive. All that really did was kind of flag for terrorists where there was something sensitive. It was kind of like, oh, there's something blurry there, maybe there's something I should blow up. But if you look here, I can't. The power plant, that was on September 11th in Western New York, that was one of the first places they locked down was the power plant in Lewiston, because you could still cause a lot of damage in this country or most countries by attacking a major power supplier. But there was a time that if you zoom to these, there'd be a big blurry spot. That's purposeful error. The original photo that was taken was fine. They would go through and make Google and blur out areas where there was a sensitive infrastructure. Like I said, I think they stopped doing that because all it did was like highlight for people where there was something sensitive. But that's an example of purposeful error. You also have, if you're purchasing data, a lot of companies have basic versus premium data. Some of the street vendors that sell GIS street data will sell a more basic version of their street data for this amount of money, but if you pay more, you get the premium data with all of their attributes. So they might actually pull the most accurate data out for people that purchase the cheaper plan, and then withhold all of their data for people that pay more money. So that, in a sense, is an operational error if you think about it. And depending on the needs of your project would dictate whether you need to pony up extra dough for the premium data plan. Sometimes data is not distorted, but overgeneralized for privacy reasons, especially in this country, which I think is a good thing. We value privacy, patient privacy, or crimes. Sometimes can be generalized. We're working with the hospital system here in Buffalo, and they had a database of people's certain diseases. Well, that's pretty sensitive data. The data was down to the address of the patient. So you don't want, GIS intern comes, gets the data. Oh, look, the lady across the street has this disease. That's her own private, that's not your business to begin with. So when that data is released, they strip the address out and they only provide it to the zip code. So all you know is, a person in this zip code 14260 has this disease. They actually remove the address data so that, because of privacy. So in a sense, they're making the data much less accurate. But I think most people would agree there's a very good reason for doing that. Or exaggeration. Exaggerating data for effect I'm going to go way back. Often with elevation, you will exaggerate in the third dimension so it shows up in view. These crime peaks are actually exaggerated, I don't know the factors, so that they show up better. That's probably not exaggerated, but often when we're looking at a 3D surface, to make the mountains or hills stand out better, the GIS analyst might exaggerate every mountain by 2x or 4x, so that they stand out. In this particular case, that looks realistic. I'm trying to quickly see. Now we're going way back. We're going backwards, not forward. That's not good, is it? You never quite know what will show up. This canyon here, this valley might not be that steep, but to more illustrate the differences in topography here, the canyon and the hills, they have applied an exaggeration factor. That was done with purpose, not by accident. Some of these things that are by accident that we're talking about in operational error, some things are on purpose. It's not by accident. It's done on purpose to visualize better changes in topography. But if you don't know that as the map reader, you might overinterpret it because you didn't realize it was exaggerated. Another cool source of purposeful error would be many street map vendors will actually introduce ghost streets to try and catch other companies pirating their data. That's kind of a cool type of error. It's called a trap street. It's a fictitious entry on a street map. And then, so if you add a bogus street to your map, and then suddenly your competitor, it shows up on your competitor's map, you know that they're stealing your map. There's an art to that. You don't want someone to try and drive down the bogus street. So often the bogus street will be in an area where it's off to the side or in a remote area where it's not going to affect everyone. And an interesting side note on the bogus streets is that for years Google had the town of Argleton, England mapped. It doesn't exist. I guess they even had restaurants in Argleton and then fake streets, fake businesses. There's no such place. This area is vacant. And Google finally removed it, but it was something that they had put in to try and trap other people from stealing Google's data. So that's a purposefully introduced error to try to look for piracy of map information. That's kind of an interesting side note. Maybe that can be our bonus question. Argleton, England, the place that never was. I'll have to think about that. So in this case, we'll talk about mistakes, but these are all purposeful errors. Whether it's Argleton or exaggerating data, removing data because of privacy, concerns with security, those are all errors that are purposeful, but if they're not clear to you as the map reader, you could misinterpret them even though they were done with a clear purpose. These type of errors, operational errors in the entry of attributes aren't purposeful. Well, you hope they're not. They're accidents that could occur that could cause problems with the error. Probably one of the simplest examples is a typo. Like I said, just typing something wrong. The person's tired, or it could either be a typo, misspelling something, adding an extra zero, or misinterpretation. Instead of calling this a desk, it's tired, I'm getting old, I call it a chair. That's a silly example, but I was out, did I miss? No, it was an exam week. I was in Florida doing mapping on Navy runways. We're mapping potential obstacles to planes taking off. But some things are pretty obvious. I can tell what a runway light is, or there's a stop sign. But there's specific military or air things that I'm not as clear on. We had a pilot there to help me. There's things called an ASIS. There's a thing called a PAPI light, which helps. PAPI light helps the pilot coming in make sure that he's at the right descent. I'm not that up to speed with that, so I could have very easily misinterpreted. Oh, that's a PAPI light. I put it in the iPad as a PAPI light, and I'm wrong. It's something else. So when people are collecting field data, misinterpretation is something that can easily occur. I think I'm looking at something, but in fact I'm looking at something else. And both of those, again, are probably accidents, but they are mistakes. It's not like this where we're purposely introducing errors. In these cases, these are mistakes that happen during the capture of data. So hence, it's an operational error. And those are both related to attributes. I'm calling something one thing when it's another thing, or I'm just typing it in wrong. You could have data entry errors with location. More often than not, now data is collected with GPS. So maybe I'm not paying enough attention to the number of satellites I have, and maybe I'm collecting data when I shouldn't be. If there aren't the proper number of satellites within view, the signal that I collect won't be accurate enough. So I could create a GPS error by not paying close attention to that. Is the GPS lab coming up sooner? Good. Hopefully by then it'll be warm. No promises this year. And you'll get some hands-on experience with GPS in a couple of weeks. Or digitizing errors. I'm going to trace these roads off of Google, and it's caffeine. I had too much caffeine today, so rather than tracing the road, I'm all jittery. That's what happened. Don't drink too much caffeine when you're going to do digitizing. There's a good tip. You're introducing error by doing that. Caffeine-induced error. That won't be on the things. Or it may or may not be caffeine. It could be other things too. So digitizing error. If you meant to plop a point, here's an oops, and you put it in the wrong spot. That's a mistake. Again, a locational mistake. We will, okay, remember our next slide. We'll get a little more specific on the next slide and talk about specific types of digitizing errors, and that's actually pretty important. These are things you'll see all the time and things you'll do all the time, unfortunately, despite your best efforts. So specific types of digitizing errors. I'm certain to ask something like this about these things. These are different ways. I only have one slide. It's actually an important slide there. These are different things that you can do when you're digitizing. So, and there are ways around sliver polygons dealing with topology. We talked about topology early in the course. So say you draw this county, and you draw it as its own entity, and now I'm going to draw, that's Erie County, I'm going to draw Genesee County. And instead of using the same line, I'm going to try and draw this Genesee County. But I didn't draw exactly the same line. You see what I did when I traced Genesee County? So notice this little overlap there? That's just called a sliver polygon. And it comes from people trying to draw two things that are adjacent, but double digitizing the adjacent line and drawing the adjacent line slightly different. Does that make sense? That produces what's called a sliver polygon. What you really should do is, rather than try to draw the whole shape, just draw the lines. Draw one line, and then use the toolbox command line to polygon to create polygons. That way you're just drawing this line once. Unless you pay really close attention to the snapping, if you try to draw over an existing line without snapping, you almost always cause a sliver. And that's remember there's a one-to-many correlation. Every shape has a record in the attribute table. Now I've created a phantom county by doing that, or two phantom counties with no information. Not only that, I've changed the acreage. That doesn't sound like much, but if it's this pipeline project I keep talking about where they're measuring, the company needs to report to the government the number of wetlands impacted. suddenly I'm under-reporting if I'm missing slivers, or I'm over-reporting if they're overlapped. So this process of trying to draw the same line twice, and it's like to create these sliver polygons. You see it all the time. The rest of these are more related. A dangling line. So you see here, this some of the different cases here. Dangling lines don't connect that should. Like I have a road here, and a road here, and they're not connecting. Those lines are left out as dangling. Now all of those things could be legit. We touched on this just a little bit earlier in the class when we talked about topology rules. I mean, this really could be two roads that end and don't touch. So in some cases, a dangle could be okay. But if this road is meant to connect to this road, that's a dangling error. And it's caused from people not drawing carefully. You're drawing it at scale zoomed out too far. Or, it's like here's Frontier Road. The Ellicott Spot campus here, and let's say you're tracing the road that leads out of Ellicott from the parking lot, and you draw it like that. That's an overshoot. You meant to have the road out of the parking lot stops at Frontier because you can only turn left or right, but you digitized it too far and you went beyond where you wanted to. It didn't snap at the intersections. That's an overshoot. You might guess what's next. It'd be an undershoot. Or you didn't go far enough. And the other, if you think about both of these also produce a dangle. I said these are more related. There's a dangle here and there. And then finally, this might be hard to visualize, an intersection. And this comes more when talking about street networks. So you have line and a regular intersection, say this is the Maple and North Forest. There's an intersection here. These are separate street segments. A person coming up North Forest can turn on to Maple or go straight. In some cases, in a road network, that's not the case. You have, Interstate 90, and you have Worley Drive and Amherst. If you see them on the map, they cross, but not really. Worley Drive goes under the thruway or over the 9. I don't remember which one. So there's no intersection. You don't want routing software to tell a user to, they're traveling on Interstate 90 to just turn off onto Worley Drive. That's impossible because it's a highway. So an error in digitizing would be to draw an intersection here. Because then if there's an intersection here, routing software would think, oh, you can turn. So that's what this last error here, intersections, means. That's a little harder to visualize than the other errors. And it'll make a little more sense when we talk about routing as an analysis in a couple of weeks. Any questions? Sampling interval is another type of error to consider, and then we'll talk about how to we call it interpolation. How to interpolate missing data in between. If we have, so here this is a map of, I can read what that says. Oh, ozone prediction map. Okay. Here's a map showing the level of ozone in California. How could this be wrong? They made this map by sampling ozone at specific locations in California, and then they interpolated it to the whole state. It's not possible to measure ozone at every single point in California. That doesn't make any sense. But the map shows all of California. They've done what's called an interpolation. I'll go back to my chemical sampling example. If the level here is 10 parts per million, and the level here is 20 parts per million, but these are the only two sample points you have, the saying, okay, so say that's Lockport, that's Buffalo, I'm going to guess that it's the level is 15 here at UB, because it's halfway between 10 and 20. That's called interpolation. that may be an error. You might not have enough points. I think this is a better example. If you can see where let's say in Lockport it's, let me do this right. In Buffalo it's 38 degrees, and in Lockport it's 36 degrees. You might claim, oh, it's probably 37 at UB. It's halfway in between. And some days you could make that claim. Sometimes that would be in it. What if there's a cold front? If it's, every once in a while this happens, it's 35 in Buffalo and 15 in Lockport. If you tried to claim it's 25 in UB, you might be wrong. There could be a cold front right here, and it could actually be 15. But in reference to the concept of spatial interpolation, you can generate error from using an improper interval. You know, this may even forget cold fronts. If most people, you might agree that the temperature at UB is roughly in between the temperature in Lockport and Buffalo. What if we look at the temperature in Cancun and the temperature at the North Pole? There's a 120 degree temperature swing between the North Pole and Cancun, and let's say UB is halfway in between the North Pole and Cancun. Are you just as confident in saying, oh, it's probably 30 in Buffalo because that's halfway between Cancun and North Pole? You probably would be less likely to agree with that because the sampling interval is not appropriate. You're taking two temperatures from thousands of miles away. You'd be much more inclined to agree when it's Buffalo or Lockport. Or even more extreme, say there's a measuring station in Amherst and one in Pendleton, and they're 38 and 36. You would be even more likely to agree that it's 37 because the sampling interval is closer. There are statisticians, some of our geologists do a lot of work with this. That is a whole extra science beyond what we talk about here, or even in GIS, to devise the appropriate number of sampling. Because you can't take it to the extreme. You can't sample every single point in nature. So we had another company help us. I think we did some sampling in the Buffalo River. And just the question of, okay, how many samples and where do we place them in the Buffalo River to get an accurate whole picture of contamination in the Buffalo River is in itself a science. And it's not even necessarily GIS. It becomes more of a statistician. There's geology, maybe more than geography involved in it because they're looking at the bedrock and sediment contamination. But it almost becomes more of a statistics problem than even GIS. You'd even see, it doesn't have to be spatial, when they do presidential election polls and they say, Obama's ahead of Romney by 4%. They didn't call every single person in the United States that can vote and ask them who they're going to vote for. They pick a representative sample. Sometimes it's amazing how they can do it. They might have only polled 1,000 people, but they pick 1,000 people that they think represent the entire U.S. population. It's remarkable to me how close they are. But in the last presidential election, a lot of people criticized, oh, these polls are crazy, they're skewed, blah, 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 and they came out almost dead on right. From just sampling a couple thousand people, they predicted the outcome of the election remarkably close. So that's another example. That's interpolation, not spatial interpolation. So choosing the right level of interpolation is important. The presidential pollster wouldn't guess who's going to win the election by asking 2 people. But they also can't afford to ask every person in the country. Somewhere in between, there's a sweet spot. And that's the science to interpolation. We will talk more. This is more of a general, how can interpolation be an error? We'll talk more about specific techniques for interpolation I think it's next week. Conversions between data sources can introduce an error. I did this myself. There's a setting called fuzzy tolerance. So basically that means if there's 2 points digitized in a data set that are within the fuzzy tolerance, treat them as 1. So if this is my square, and my fuzzy tolerance is this, 8 inches, when you edit the data, it'll say, oh, this really is 1 point. It would collapse them down. That might be wrong. I may have wanted those 2 separate points. So normally the fuzzy tolerance is really low. So to illustrate what the problem that could cause, I set the fuzzy tolerance artificially high and did conversions on this set. These are the 1990 buildings. And after running a couple edit sessions, I started to get triangles because the fuzzy tolerance was too high. It was taking 2 corners of buildings and treating them as 1 point. So geoprocessing techniques can also introduce error. I introduced error by having the tolerance between points too high. I did it purposely to make a slide for the class, but it's something that could also happen by accident. Comparing this is related to the sliver polygons example I mentioned. You have to be careful about overlaying data that was digitized at different scales. Remember that slide, the first slide after break, where the map accuracy varied wildly based on scale? So here we're taking 2 city polygons representing the same thing, digitized at different scales, overlaying them, we have slivers all over the place. We'll talk a little bit, one more minor topic, and then we'll be done soon, I promise. We'll talk about metadata. And this is a good point to introduce metadata. Metadata is data about data. And it should be the responsibility of those who create data to provide the relative information about data. So in essence, it's data about the data that will help people use it. Think of all the different errors that we talked about tonight. Wouldn't it be good if you purchased or get a data set if you knew all that? Like the 1990 buildings example. If you know that no building since 1990 was traced, that helps you decide whether you can use the data and how to use the data. Things like that would be put in the metadata. So metadata is a file that travels along with your GIS data that explains its usage. Am I going to the New York State house? They're supposed to require metadata. They don't. For example, this is a data set you can download from New York State. Lakes and ponds in Cayuga County, New York. This is a metadata file, and it contains information about that GIS file that helps us make decisions. For example, who created the file? In this case, it was Department of Planning in the County of Cayuga. There's an important one. When was it created? Now, 2001. Now, in the case of lakes and ponds probably don't change that much, so that may not matter. But where was it created? In Auburn, New York. It's vector, not raster. Where can I download it? Information about it, lakes and ponds within Cayuga County. So we talked about the area of the map being potential error. This does tell me it's the whole county. Hopefully from the slides that I've shown you, that's an important one. The data was compiled at that scale. So now you know the scale at which this data was created. And you can compare that to, in fact, they would say it was created off of paper 1 to 4400 flawed maps. We looked at those earlier today, remember that? So now we know the source of the data, so you can use that information to determine whether this GIS data set will meet your needs. Supplemental information, lakes extending beyond the county have been clipped. So if the lake goes outside the county, they cut it to the county boundary. So that's something you might want to know. The borders of the data set, it's updated as needed, keywords. This is important, questions about the data. Here's a phone number and an email. If you encounter a question about the data, those are the type of things you see in metadata, a contact person, and so on. Sometimes metadata has too much information about the attributes. The attribute name indicates, not surprisingly, the name of the water body. The attribute area, that might be good to know. They note for us that the area given is in square feet. There's the contact information. See, they can overdo it. Nick shows up here again because the first one was the person that created the data. This is the person that distributes the data. So I guess it could be a different person. See what these associate GIS analysts. Sometimes this scares people off because there's so much information. But I think if you think about some of the stuff we talked about today, I think you can see where the metadata file would be useful. So that's a good real-world example. The slide also has the contact information, how current is the data, how accurate. The example had all those things, explanation of attributes, and so on. So that's a good question sometimes is what are some things you might find in metadata? And hopefully now you see the importance. It's an easy thing to forget. I can sit up here all night and say, oh, you should always fill out metadata, but I don't. Hopefully you won't go check my data sets. Because it's an easy thing to skip, because often it's done at the end of a project. And it's forgotten. You even saw there I had to click a couple times before I found one with it included. But it is something if you're creating data sets that should always be included. And just, we'll whip through these last couple slides. In the U.S., the Federal Geographic Data Committee develops metadata standards. That web page that you saw with the list of attributes, the FGDC defined how that page is laid out, what attributes are on it, and so on. That's all. Other components of metadata, what is the positional and attribute accuracy? I think we saw that listed there. Lineage, how was the data, what source data basically does that mean was used? And is it complete? I think it did note that it covered the entire county. But to say they didn't end up tracing water bodies in the whole county, that's where they would note that. So just, not a big deal. This just shows, I think we discussed this already, that when you might see some metadata refer to a 90% confidence. And when you see that, what that would mean for a 1 to 24,000 foot map, there's a 90% chance that the point is within 40 feet of where it says it is. 10% of the time there's some other error caused it to be even further away, even though it's digitized at that scale. So some of this actually overlaps what we already talked about, so we can go through this pretty quick. Attributional accuracy might be mentioned in metadata to indicate how close the values are to reality. And if you think about that in terms of locational attributes, or this with locational accuracy, there's 4 potential things. You could have a point in the right location and is correct, or you could have one of the two. So both location attributes are right, or they're both wrong, or just one of the two are right. Conflation is the act of, and this can happen, you have 2 data sets. One is locationally accurate, one is attributionally accurate. So you have this person's version of the street is dead on right. They've traced it off a photo, it really curves like that. But they don't have much information about the street. Person number 2's street does that. It's not as locationally accurate, but you have more attributes about it. It's Main Street and so on. So conflation is the act, and there's some tools in ArcGIS to help with this, of taking the best of both data sets and combining them. Obviously that could introduce some error if you think about it. So taking the attributes of Main Street and attaching them to this more spatially accurate line. When the NFTA here in Buffalo first started using GIS for mapping their buses, they caused a problem doing conflation because the streets in Buffalo aren't that far apart. They shifted all the attributes over a block. So say Delaware, if that's the good version of Delaware and Elmwood, the conflated data set from the US Tiger, we'll talk about that, was more than one street off, so it took the attributes of Delaware and attached it to Elmwood or Franklin because it was one street over. So conflation can also be a source of error. And so for a brief period of time, they first put the street data in to monitor bus drivers that they were following the proper routes. So for a brief period of time, bus drivers were getting in trouble. You were driving down Elmwood. No, you weren't. No, I wasn't. Yes, you were. Turned out the bus driver was right. I'm more interested in what we talked about a few minutes ago than this, but logical accuracy, how well are relationships between features maintained? Is topology accurate in geometry? Was the proper geometry? We talked about topology earlier. Completeness. The Cayuga County layer says it's every water body in Cayuga County. Is it really? How many are left out? And are the attributes filled in? Are too many attributes blank? And this slide has a lot of stuff on it. The key would be more, is the level of detail of the attribute complete enough for your analysis? Say, I should simplify this. Say the data set only contains whether it's forest or agricultural. But perhaps, for your project, you need to know more detail. So the level of detail is good to note in the metadata, and it's good for you to review. We have had this problem. We were studying for a new potential Navy runway in North Carolina, and they were concerned about tundra swans, which are threatened. Tundra swans winter there, and they prefer, gosh, I don't remember. They prefer a specific type of crop. All the data that we purchased or downloaded for land use in that area just said agricultural. So for our purposes, the data wasn't wrong. The fields were agricultural, but it wasn't detailed enough of a description. We were looking for a specific type of agriculture, and the data didn't go to that level of detail in the sense of the attributes. So we had to actually send field teams out to review the data, review the field, and see what kind of agriculture is there. Lineage, I'm not worried about the last slide. And I think we're good.